Good morning, students. In today's session, we will be overlooking the storage allocation and management techniques related to the effective use of the memory of the computing system. So basically, as we know that the memory is a collection of bytes or words. Every cell in the memory has a particular address. So these storage locations are basically used to store the different types of processes which are ready to be executed by the processing unit. So at the very basic level, there are two different types of storage allocation mechanisms which we have in our disposal. Among the first is called the contiguous storage allocation, and the second one is non-contiguous storage allocation. So what does that mean? Uh, Contiguous storage allocation means the contiguous storage allocation actually means that the entire process is being stored at a particular consecutive locations of the memory. And in case of non-contiguous storage allocation, parts of the processes uh, may be scattered throughout different parts of the memory. So these are the very basic differences between contiguous and non-contiguous storage allocation that we generally use for the memory management. As I told you, what is contiguous storage allocation? Contiguous storage allocation implies that a program's data and instructions, they are assured to occupy a single contiguous memory area. Contiguous memory area means continuous locations in the memory. And also contiguous storage allocation can be further divided into some fixed partition storage allocation strategies and variable partition storage allocation strategies. So in today's session, we will not be focusing on non-contiguous storage allocation, but we will focus our discussion on various concepts related to the contiguous storage allocation mechanism that we employ in case of memory management. So if you consider the present slide, you can see a diagram there. There are three job queues and there are three different sections of the memory. They are termed as partition 1, partition 2 and partition 3. In case in the partition 1, there is a particular queue of processes to be given memory storage locations. Same for the partition 2 and partition 3. Now, what happens is that processes with small address space use small partitions and processes with large address space use large partitions. So this is known as the fixed partition contiguous storage allocation scheme. Now, uh, take the reverse case. That is, let's say a very practical. Let's consider a practical example here. Suppose you are traveling with a particular vehicle, say a two-wheeler, and you want to park it at a particular place. Now, when you are entering into the parking zone, you can see that there are several open spaces between between two parked vehicles, but that location is not adequate or enough to park your own vehicle. That means you have to search for the exact place where you can park your vehicle. But you can easily see that there are at places there are considerable amount of space between all the parked vehicles. But in this case, what happens is that there is some sort of wastage that we can see. So basically, this notion is derived from parking of vehicles on the sides of the streets where the one who manages to enter will get the space. Say two vehicles can leave a space between them but that cannot be used by any other vehicle. So this means that whenever a process needs memory, a search for the space needed by it is done. So if contiguous space is available, then only the particular process will be allocated and it will be loaded into the memory. Now see, this particular scheme generally has some limitations. What are those limitations? You can very easily say that some sort of wastage of memory spaces are being encountered here. That means there should be some mechanism by which we can avoid this wastage to the extent that is possible for us. And the other technique, that is the non-contiguous memory allocation, does just that. So basically, in case of non-contiguous memory allocation, uh, generally we try to minimize the wastage of memory spaces, and a particular process can be scattered. A particular process can be allocated memory spaces, but that memory spaces need not to be continuous. They can be scattered. So that is the main concept here. So we will proceed here in the next slide. Now see, in the phenomenon of entering and leaving the memory can cause the formation of some unusable memory holes, just like the unused space between two vehicles. So in the preceding example that I told you, so you can easily see that there are definitely some free spaces between the parked vehicles, but they cannot be used. But they cannot not be used effectively. Now, if you take that analogy to computing to the storage allocation problem, so those wastage of spaces are termed as external fragmentation. That means the memory is being scattered. The memory is a collection of some scattered locations. So the memory is a collection of some unused holes, we can see. We are not effectively utilizing the entire storage location of the full memory. So there are some specific free spaces available, but so that concept is known as the problem of external fragmentation. Now there are three particular strategies to allocate memory to this variable partition scheme. I already told you that memory can be that you can use fixed partition scheme or variable partition scheme. Now, in case of contiguous allocations, in case of contiguous allocations, we can be using both the strategies. Now, in case of variable partition scheme, there are three strategies that we can follow. Those strategies are best fit, worst fit, and first fit. So let's see what is the concept of these three strategies. Now, in case of the best fit mechanism leaves small sized unusable partitions or holes. In case of how the best fit strategy works, best fit strategy place the process in the smallest possible hole in which it will fit. That means there will be numerous types of unused holes available in the memory, and the best fit strategy tries to place the particular process in that hole which will leave the smallest amount of unused space. So you can see here a particular free memory list is being kept, and the starting address of those memory locations are being denoted by the letters E, C, A, and G, and their length are also been specified here. Uh, Starting location E has a length of 5 MB, C has a size of 14 MB, E has a size of 16 MB, and G has a size of 30 MB. Now see, a particular request comes for a memory space of 13 MB. That means there are there are three possibilities here. Either you can use the particular location which starts from letter C or letter A or letter G, 14 MB space or 16 MB space or 30 MB space. Now what happens is that if you place the particular process in the particular location having a size 14 MB, that means only 1 MB gets wasted. So it is better to allocate the unused space which starts at the address C, in this case that is 14 MB. So that is shown via the diagram. So in the memory, so in the extreme right, you can see the memory spaces. The at the very top we have the operating system installed in the memory, and then you have the different user processes and some unused holes of different sizes. So by this strategy, you can minimize the concept of wastage of memory. It's one of the best techniques to oversee the problem, to overcome the problem of memory address wastage. Now, another technique is the first fit. What is the first fit? That is, chooses the first partition whose size is greater than or equal to the requirement. Now, in this case, first fit strategy, how it works, it places the job in the first memory hole on the free memory list in which it will fit. Now here you will search the free memory list to get the particular size, and whenever you get a particular free memory space that is greater than equal to the requirement, you allocate the process that particular memory space. So in this case, now in this case, you just see that the starting address location starts from ADR, and it has a length of 16 MB, and our requirement is 13 MB. So search starts from that place. So that is the first location that is being searched, and it is greater than or equal to the requirement. So the process is being allocated the particular slot there, which starts at the address location A, and you are getting a 16 MB hole there to accommodate a 13 MB process. That means 3 MB again gets wasted here. But that is the concept of first fit strategy. Though that means the thing is that first fit strategy can be implemented very fast. You don't have to search the entire list. Whatever first memory location you're getting that is fit for the requirement, you are just allocating that particular location to the particular process. That is the concept of first fit. And then we have the worst fit. Now what is worst fit? It is easily recognizable from the name itself. Choose the largest partition and allocates it to the process. It can leave bigger unused memory locations in the system. So again, we have the free memory list here. The starting address and the lengths are given, and in the worst fit strategy, it works like this: place the process in the largest possible hole in which it will fit. Now, the particular free memory list is kept here in the descending order by the hole sizes. So you can easily see from the example shown in the slide that you are getting a request of 13 MB, but among all the free memory locations, the maximum sized location is 30 MB, and you are allocating the process to the particular memory location which starts from starting address G. Now, the whole size is 30 MB and your requirement is only 13 MB. That means a huge amount of memory space gets wasted. But still, it is one of the three possible strategies to oversee the memory allocation schemes. So it is also used at some places. Now these are very common three strategies. You have to mix and match, and you can use all those three in a mixed manner. Now a particular concept is there which is called compaction. What is compaction? Basically, when you are using a particular memory space, say there are several processes been getting allocated memory spaces, and they will be leaving the memory when their work finishes. So at a particular random amount of time, there will be multiple free blocks available as a part of your memory, but they are not contiguous in size. That means they are being scattered throughout the entire memory. Now, if we can collect all the free memory spaces at one location, then what will happen? We will be getting a huge amount of contiguous memory space which is available or which can be allocated to other processes in need. So basically compaction means to move the processes in the memory in such a way that scattered pieces of unused or the free memory can be placed together so that any other process demanding contiguous memory for it can use it. So you can easily see the from the diagram here, there are two memory segments being shown before compaction and after compaction. So in case of before compaction, at the very extreme left position of the slide, you can see the free blocks are being scattered, and at the extreme right position, you can see that the free memory holes are being aggregated at one particular point only, and that is creating one large free block. Now, these particular large free block can be allocated to other processes, whoever needs it. So basically, we are getting a contiguous free storage locations in our disposal now, and we are using the concept of compaction here to achieve that. Okay, with that we will be closing our today's session here. In the coming slides I will discuss some other aspects of memory management techniques. Thank you.